MIT physicists have developed a protocol to verify the accuracy of quantum experiments. At the scale of individual atoms, physics gets weird. Researchers are working to reveal, harness, and control these strange quantum effects using quantum analog simulators, laboratory experiments that involve supercooling tens to hundreds of atoms and probing them with finely tuned lasers and magnets. Scientists hope that any new understanding gained from quantum simulators will provide blueprints for designing new exotic materials, smarter and more efficient electronics, and practical quantum computers. But in order to reap the insights from quantum simulators, scientists first have to trust them. That is, they have to be sure that their quantum device has high fidelity and accurately reflects quantum behavior. For instance, if a system of atoms is easily influenced by external noise, researchers could assume a quantum effect where there is none. But there has been no reliable way to characterize the fidelity of quantum analog simulators until now. In a study appearing in the journal Nature, physicists from MIT and Caltech report a new quantum phenomenon. They found that there is a certain randomness in the quantum fluctuations of atoms and that this random behavior exhibits a universal predictable pattern. Behavior that is both random and predictable may sound like a contradiction, but the team confirmed that certain random fluctuations can indeed follow a predictable statistical pattern. What is more, the researchers have used this quantum randomness as a tool to characterize the fidelity of a quantum analog simulator. They showed through theory and experiments that they could determine the accuracy of a quantum simulator by analyzing its random fluctuations. The team developed a new benchmarking protocol that can be applied to existing quantum analog simulators to gauge their fidelity based on their pattern of quantum fluctuations. The protocol could help to speed the development of new exotic materials and quantum computing systems. The new study was motivated by an advance in 2019 by Google, where researchers had built a digital quantum computer dubbed Sycamore that could carry out a specific computation more quickly than a classical computer. Whereas the computing units in a classical computer are bits that exist as either a 0 or a 1, the units in a quantum computer, known as qubits, can exist in a superposition of multiple states. When multiple qubits interact, they can, in theory, run special algorithms that solve difficult problems in far shorter time than any classical computers. The Google researchers engineered a system of superconducting loops to behave as 53 qubits and showed that the computer could carry out a specific calculation that would normally be too thorny for even the fastest supercomputer in the world to solve. Google also happened to show that it could quantify the system's fidelity by randomly changing the state of individual qubits and comparing the resulting states of all 53 qubits with what the principles of quantum mechanics predict. They were able to measure the system's accuracy. The researchers wondered whether they could use a similar randomized approach to gauge the fidelity of quantum analog simulators. But there was one hurdle they would have to clear. Unlike Google's digital quantum system, individual atoms and other qubits in analog simulators are incredibly difficult to manipulate and therefore randomly control. But through some theoretical modeling, the researcher realized that the collective effect of individually manipulating qubits in Google's system could be reproduced in an analog quantum simulator by simply letting the qubits naturally evolve. The researchers hypothesized that if they could develop a numerical simulation that precisely represents the dynamics and universal random fluctuations of a quantum simulator, they could compare the predicted outcomes with the simulator's actual outcomes. The closer the two are, the more accurate the quantum simulator must be. To test this idea, they teamed up with experimentalists at Caltech who engineered a quantum analog simulator comprising 25 atoms. The physicists shone a laser on the experiment to collectively excite the atoms, then let the qubits naturally interact and evolve over time. They measured the state of each qubit over multiple runs, gathering 10,000 measurements in all. The researchers also developed a numerical model to represent the experiment's quantum dynamics and incorporated an equation that they derived to predict the universal random fluctuations that should arise. The researchers then compared their experimental measurements with the model's predicted outcomes and observed a very close match, strong evidence that this particular simulator can be trusted as reflecting pure quantum mechanical behavior. More broadly, the results demonstrate a new way to characterize almost any existing quantum analog simulator.